Okay. Hi, everyone. Welcome to the next installment of the NLG seminar. Today we have Shayne. Shayne is a PhD candidate at MIT whose research investigates the intersection of AI and its global impact by developing data-centric methods for system building and auditing AI's influence on the web, economy, and society. He leads the Data Provenance Initiative and has contributed to training models such as Bloom, Aya, and FLAN-T-Fi or PaLM. His work has earned Best Paper Awards at ACL 2024, NACL 2024, and has been featured in prominent outlets including the New York Times, Washington Post, The Atlantic, and MIT Tech Review. Without any further delay, Shayne, all yours.
Thank you for that very formal introduction. I have to live up to it now. But thank you all for joining this talk. I want to make it pretty interactive. So I want to start by asking, feel free to just say, raise your hand in the crowd or on Zoom. Who here has trained a language model before, out of curiosity? Cool. Okay. Who has trained a multilingual model before?
Okay.
Maybe is that one hand or nobody? I can't
Yeah.
tell.
Yeah, I think that's one. Yeah.
Okay. And presumably all of you have trained models where there are many different sources of data. And so the point of this work is to think about multilinguality as a sort of first-class principle. Rather than just training a model for scale or for largely English benchmarks, what if you wanted to train a model for Swahili or Thai or German or Arabic, and or a mixture of those things. And so essentially, we take the scaling laws paradigm and we adapt it to the multilingual paradigm. But the important thing about this is that the concept of having many different sources of data and targeting one of them as your evaluation is something that appears across machine learning. And so data mixing and scaling laws, when you have many different data sources that have different constraints, is something that I think the methods might generalize to more broadly than just the application of multilingual AI. So I think this could be applicable to just about anybody that's building or training models or wants to think about the best way to train them. So I want to start quickly by motivating this work, and then I'm going to jump into four of the research questions that we answer one by one before bringing it all together. So this paper will be presented next month at iClear in Brazil, and it was released late last year with my colleagues from Google Cloud and DeepMind. And I want to point out this was really hard to publish. We could not publish the data splits or well, the full pre-trained data set is public, but we couldn't publish the models or some of the results of the models because this was something like 800 separate pre-training runs across 10 million to 8 billion parameter models. It's very big. And I think it's a very valuable resource for the broader community. But let me motivate this a little bit. Aside from this being about broadly how to compose and mix different data sources when you have different targets in mind, I want to point out that 99% of all scaling laws research, and I did a thorough related work background review, and my colleagues did as well, almost all of it treats English as the objective. Either it's all English data or primarily English data, or the evaluation objective is English. And so what we wanted to do is build out the methods and infrastructure to understand how to compose, scale your data, whether to pre-train off of a multilingual checkpoint or whether to fine-tune when your goal is non-English. And this has relevance to data sovereignty and AI sovereignty. Can we predict the limits of AI development right now across different languages based off of the amount of data that's available? So I want to jump into an example. So Thai has, I think, about 70, 80 million speakers in the world. And for most of them, it is their first and primary language. But the thing is, even though it's such a well-represented language from a very big country, if we compare the amount of data available to Thai compared to, let's say, English, if we look at MATLAB 400, this is Google's last large, well-curated, deduplicated pre-training corpora that they released based off of Common Crawl. in I think 2024 or 2025.
Charts.
Let's say there are, however many English tokens in it. There are only 16% the number of tokens for Russian as there are for English. Only about 12% for Spanish as there are for English. And by the time you get all the way down to Thai, at 26th spot, there are about 0.6% the number of tokens as there are for English. So what does that mean? What that means is that if you take a model like ChatGPT or Claude or any others, they probably, although they're not transparent about it, they probably uniformly sample according to the availability of data. So we can imagine that most of their training data is in English, and then it follows French, Spanish, Russian. And even if they're upsampling the low resource languages, Thai is likely to be a very tiny sliver after many other languages take priority. And so the performance on Thai for this model is going to be pretty poor, just objectively. But what if we just were to train a model monolingually on Thai? What we would see is that because there's so little Thai data, that if we had a large model, we'd be repeating many epochs like we see here with the dash lines. And so we'd see it again and again and again. If we learned anything from the scaling laws papers that came out in 2022, 2023, we know that after you hit about 4 epochs of language data, you start to hit diminishing returns. So if you train just on Thai, it's going to memorize all this data. It's going to hit diminishing returns by the time you hit 8 to 16 to 32 epochs, and you're not going to learn anything new. And so the performance on this is arguably not going to be any better than what you would see for a large model that trained across many languages and had some positive transfer between them. So what do you do to get a good model for Thai? And the answer, if we're to look at the solution, look ahead, is that optimally it'll probably look something like this. You'll train on Thai primarily, but not so much, given that it's constrained, that you run out of this way, that you hit diminishing returns. And then you're also going to have lots of beneficial related languages. And related or beneficial languages could be languages like Indonesian, Malay, Lao that are similar from similar language families or use similar scripts. Or they could be languages like English and Spanish that just happen to be very heterogeneous and of high quality and have lots of content that makes them useful to many languages. But the question is, how do you get to this mixture, and how do you figure out that this is the best mixture to get the best performance on Thai? And I'm going to take you on that journey in this paper. But before I do, any questions on this setup?
So I guess maybe it's too specific to the table at hand. Firstly, I'm very surprised that you don't have more Chinese in this.
Mm-hmm.
Like quite surprised by that. So is this like, and I guess this relates to the higher paradigm as well. Is the percentage spread of language more a result of the availability of it or active decisions when it comes to how we curate it?
Both. That's the key. It's a phenomenal question. It both matter, and both are things that we labs are trying to optimize for. They're trying to get more data, and they're trying to curate it better. My colleague on the paper that actually built MATLAB 400, I forget the reason she gave exactly, but the reason that there's not as much Chinese as you'd expect from this common curl dump that they've curated is because they found a lot of duplication and content that was lower quality that didn't reach the bar, at least for Google's Chinese, quality filters that they had. So I suspect Google or other companies would have more Chinese data they've purposely collected, but more or less, the distribution of this data roughly follows what you would see from the content on the web after some level of curation that was near state of the art in 2024.
Can I ask a question? Can you hear me?
Yes, I can.
Do you guys do like as a pre-processing like romanization or those kinds of things? Like it's not strictly like, I don't know, Vietnamese letters. It's like English characters representing the language, right? Is that what's
Uh,
present in this data set?
no, so there are many different scripts involved.
Okay.
It's not all in the Latin script. So I could look at the list, or it should be in the paper, but
Mhm.
not only are they from different language families, but like I think it will be in its like native script. Some of them have been changed to Latin or Romanized, but our vocabulary also accommodates the full range of pre-training data.
Gotcha. And I guess maybe you'll get into it, but I'm just curious about what kind of tokenizer training you do to make sure that vocabulary is robust for different languages.
Yes,
Like,
good question. It's in the paper. I can pull it up. I was not on the vocab part of it, but it was a strategic decision to pick something with back off to bytes, but also it was trained across like a sample of the full multilingual data, and the vocabulary was made to be fairly large. There was a vocabulary size scaling law paper that tells you based off of the size of your model, the number how much data you have and multilinguality, how big your vocabulary should be, and we picked something um, that was much bigger than it needed to, that we thought it needed to be based off that paper to accommodate the range of different things. So it's not perfect, I'll say that, but we did do the best that we could to take that into account.
I guess the question is like when you train your vocabulary, is it affected by your data mixture? Like, do you already consider the availability of different languages out there, or it's separate from what you have? Because
Good.
that basically couples your decisions.
Yeah, so good question. In some experiments, we used a monolingual vocabulary, and in some experiments, we used a fully multilingual vocabulary. I think some might have been bilingual, but we did modify it according to the experiment. And I'm trying to remember now, but each set of experiments will state which assumption, and it is a factor that we try to account for as well.
yeah.
It'd have to depend on the individual experiments, but yeah, maybe we can zoom into that a little bit more when we get closer to it. But great question. Um, okay, let me move along a little bit, so I think we have a good idea of the setup. So
Yep.
the first thing that we wanted to do, to just remind us, we want to get this optimal mixture. We want to understand for Thai, if the target, how beneficial is it to train with English, with Indonesian, with Malay, with Telugu, with any, Swahili, any language that we might have? And so the question is, how do we measure language synergies? And linguists have thought about this. People have thought about from like a language symmetry or sorry, like how close are the language families, things like that. But we're not asking how close are these languages in terms of their structure or their composition or their culture. We're asking empirically, based off of what is available on the web and to the greatest extent of the availability of that data, and after it's been curated by state-of-the-art methods, how beneficial is it to train with for the target? So if you, let's say, this is a learning curve, and we want to measure over the training steps how the loss changes for Thai, we could train a model just on Thai, and it might look like this. And then we could train models, bilingual models that are each batch is 50% Thai, 50% Indonesian, or 50% Thai, 50% English. Or 50% Thai, 50% Telugu. And I've looked ahead. I know Telugu is like the worst language for Thai, but you can see a pattern here. The worse we know that if the learning curve is higher or off to the right, then it's worse for this language. And so essentially, the bigger the gap between this learning curve and these learning curves tells us something about how good or bad it is for Thai.
A
And
quick
so
question on how you determine like the elbow of the curve, because it could be a little bit arbitrary, like what you define as that point you're comparing across.
the elbow being this line
Yeah,
where we would,
exactly. Like
Like the x-axis?
yeah, like so there's a delta, right? I think I saw this in your paper. Like there's a point that you choose on the curve that represents
yeah,
like an actual validation loss for the language, right? Just
yeah.
curious how you choose that in a principled way, because yeah, that's tough, I
So
think.
good question. So we ended up picking about 10,000 steps after looking at lots of curves and
Mhm.
saying, okay, they seem to have started to converge towards where they're going to go at that point in time, rather than picking something up here where it's more unstable, or too far
Yeah.
ahead where we couldn't get all the data because you have to train this one forever to converge. But
Mhm.
what we also did to verify this is we actually took all of the data across, all the way from here, all the way down to the fullest extent of how long they're trained for, to look at the dynamics of this distance and how this distance changes over model size and over where that elbow point is. And so we were able, it's in the appendix, but we were able to confirm sort of that relationship persisted. And you're right that different elbow points, you will see some variation between, how beneficial English is if the elbow is here versus here relative to other languages. But over the long run, we picked something that allowed us to be as far down the curve as we could while being able to see as much data as, while all these things will have reached that loss. And that's hard because you have to train this one for a long time. So it is a little bit arbitrary, but you're able to substantiate it by putting all the data across. We evaluate, every, 500 steps or whatever here. You can see
Yeah.
everything and adjust for that.
So maybe you'll get to this, but for each of these, are you using the same number of tokens roughly, or like the same amount of data, or inside this is like the Thai thing you're looping over and doing multiple epochs just to hit that number of training steps?
Good question. We are doing the latter. The point is not to pretend that we have equal amounts of English as Thai, because we don't. So we are essentially doing the looping for the languages where they hit constraints, because in reality, they hit constraints. And we want to show there's limits to how much they can benefit the target language.
Got it. Okay.
I guess an ablation to what DJ was describing is if for the language that you have the least of, like cap the other languages at that limit and do the same kind of epoch looping.
Yeah. But I guess the argument is that you're taking into consideration the natural frequency of those things on the internet as well, right?
Yeah.
Yes. What you're saying is a great experiment and something we thought deeply about, but when we were deciding how to allocate the compute, we decided not to do that. And
Secondary. Yeah.
the decision was basically because inside Google, they said, we don't want to know if we did have infinite Swahili, what we would do or how useful it would be. We want to know based off how much we actually have. And
Makes
so,
sense.
yeah. So if you just look at Thai and English, and yeah, thank you for also taking a look at the paper in advance. But we pick our elbow point, and we look at the loss where this curve, what loss it reaches at this number of steps. We draw that line across, and we look to see where this curve intersects. And you don't have to dive into too much detail, but we're able to formalize a bilingual transfer score, which is basically saying we're measuring this delta. And the smaller the delta, the better, more positive the score is. Whereas the broader the delta, the further away this learning curve is, the score ends up being negative, in particular if it's past this 2D line. So we do that many times. And I'm going to gloss over some details because we do many things that allow us to extrapolate the bilingual transfer score to 38 by 38 languages. But in short, where you see red, it means there's a positive synergy at this model size. And where you see blue, there's negative transfer. And it makes sense, at least from our, look. Remember, there's no gold truth here. There's no gold truth. We're just empirically measuring and then eyeballing and thinking that from all our measurements, we hope that this gives us the best representation of usefulness. And I think it does. So for Spanish, which is this line here, the most useful language, we go down empirically, is Portuguese. That makes sense. Followed by Catalan, that makes sense. French, and the least useful ends up being Japanese, which has a different script, different language family, completely different, and that seems to make sense. And we look at Thai, we look at many languages, and it's really interesting. And one thing I'll point out is that English actually is frequently the most useful language for everything because of how plentiful it is, because there's lots of high quality, because we've curated the filters and curation steps to make sure that its data is more curated than data in other languages. And it's interesting what other languages frequently appear. I think it was French and Hebrew and Spanish are frequently beneficial across other languages. But before I go to the next slide, I want to ask you all a quick poll. Raise your hand if you think that this matrix is largely symmetric.
Symmetric.
Which means that if Spanish is helpful for Catalan, then Catalan is helpful.
No, it's not. Yeah. I mean, like, I guess the thing that makes me think it's less symmetric is that like blue bar that's
Yeah.
horizontal. Uh, if that was like if it was reflective across the diagonal, then yes, but like it doesn't seem to be that symmetric.
You
Yeah,
guys
which is kind of
are
surprising.
You're
Yeah.
smart. You got it. Yes. So I can't fool you. I fooled others on this before because people want to think, oh yeah, it'd be symmetric. And many people intuitively, if you don't show them this chart, they will think, obviously, I did some experiments to show that this language A was helpful for language B, so probably the inverse is a good bet.
Yeah.
But it turns out that's not the case. If all the lines were along this dotted dash line, then it would be the case. But we actually see that there's sort of this branching effect that shows that the symmetry isn't true. And I was surprised by this, and I think a lot of it comes down to English can be helpful for Thai, but Thai won't be helpful for English. And some of that is the quantity, but some of that is also the amount of curation and other things like that.
Quick question.
Yep.
Can you hear me?
Yes, I can.
For the previous slide, were there any like instances where you were surprised by the negativity or positivity of transfer based on the relationship between the languages that you can remember?
Um, I think there were some surprises, yeah. Like Croatian and Swedish turn out to be a little bit beneficial for Thai. And I was a bit surprised by that. I think there are some things that don't make like obvious intuitive sense from thinking that the languages are similar.
Gotcha. And also for this, did you guys include any Creole languages?
Great question. I would need to check across the 38. I don't remember them all off the top of my head, if I'm being honest. There might be one or two, but honestly, also maybe not. I'd have to double check.
Okay, thank you.
Yeah, no, thanks for your question.
So actually, sorry, before we move on, I guess I had a clarification question on the way you handle the sampling between languages when you're mixing them, right?
Mhm.
So let's say you're doing a Thai plus English run, right?
Yeah.
You use all of your Thai and all of your English. So just to check, when you are trying to achieve a particular number of training steps, the sampling ratio between Thai and English, does that say the same? So like I guess it's basically that like you're, let's say there's 100 times as much English as Thai. When you do
Yeah.
a Thai plus English run, you're 100 English and one Thai into how many ever like loops you need in order to reach that training step.
Think of it this way, every batch is 50-50, and Thai will end up looping faster than English.
I see. Okay. Okay.
So if
That
10,000 steps, 5,000 is Thai. You make up that 5,000
That makes
Thai by
sense.
looping. Yeah.
Got it. Got it. Okay. And like I take it you're mixing it together within a mini batch, or like is there a curriculum here?
No curriculum.
Okay, cool. Thanks.
And
Yeah.
I think this is just one. So you just train on one language, right? And then just see the validation on the target language. Is that correct? For this cross-lingual transfer?
I thought it was you train on a mix and you look at the validation on one.
So the real
Okay.
answer, and it gets more complicated, is for within this box here, the
Yeah.
like 10 by 10, we do the bilingual transfer score.
Uh-huh.
But it's really hard because this takes like to do monolingual is 10, but then 10 by 10 basically you have to do a bunch more to do, or every binary combination. I think it's like 45 extra or something. So
Yeah.
it becomes inordinate to do that many pre-train runs for all this. So what we did is we trained multilingual models, and then we continued pre-training with just one language and saw how the loss changed relative across other languages. So you train with Thai,
Makes sense. Yeah.
and you would see which languages went down the most and which ones went up the or didn't go down the most. And then we basically created a function to map those scores to these types of scores, which we thought were more stable, and to predict these across like all of the data that we had available here, not just one elbow point. And
Yep.
so, yeah, there was a little bit more under the hood to make that work. Good question again.
Gotcha.
I can ask one more follow-up question of you guys. Do you think, and this goes back to your question earlier, do you think that language A helping language B, do you think it's more likely to help if the language script is the same or if the language family is the same?
I'd say script.
Yeah, because like that's how the model sees
tokenizer,
it.
right?
Yeah.
All
I would
right,
say
you guys are on a roll. So these are like quartiles. My colleague said these are statistically significant after evaluation, even though the medians look very close. But same family and same script obviously helps the most, and but script is even more beneficial than family. Okay, so for the next step of the paper, we have all these synergies. You have this matrix saying how similar we think empirically language A is, or how beneficial, I should say, language A is to language B across many languages. But that still doesn't tell us how to estimate the loss, how to create a scaling law, or the best multilingual mixture. So we need to fit scaling laws. But the problem is that if we look at chinchilla scaling laws, there's only one D. And so, but we have many data sources. And so it's not really helpful for our multi-source setup. And I'll quickly go over the chinchilla setup here, but basically this is your observed data in pink. You have your model loss, and you have model size, and you have data size, and you can do many experiments to observe how many tokens you've seen at this model size to get that loss. And then you fit these learned coefficients and exponents and this irreducible loss to sort of parameterize the loss based off this. And then your compute budget, if you want to constrain how much compute you have, you can then work out the best model size and best data size to get the best loss. But as I mentioned, we only have one D. And so I looked at many different formulations for this, but the goal is to do something that one was simple and elegant, easy to understand, because I don't think you need something highly complex to solve these problems. You'd rather it be simple and understandable. I wanted to follow the existing chinchilla symmetry between the model size and the data size. It's worked very well. And I wanted something that took into account data constraints. So it would model explicitly the diminishing returns of, when you have multiple epochs of one data of a certain data source. So it's got to be multi-data source. It's got to take into account diminishing returns from doing multiple epochs on one data source. I want it to be able to fit the scaling law in one run. Some scaling laws you have to fit in multiple different runs where you fit some parameters than others. It gets more complicated. It's just like more overhead. I didn't think that it needs to be that complicated. And I want it to be effective if your observed data, for example, for Swahili, we only had observed data for when it did one or more epochs because it looped so quickly. Whereas for English, we never got above one epoch. And so some scaling laws it requires that you have data before and after one epoch. And so we want it to be more robust to whatever setup, given that we're working with languages that have very different constraints. And so the way that we did it is we took this D and we split it up into three additive components. The effect of the tokens from the monolingual source, the effect of the tokens from the transfer languages that we figured were closest or most prominent based off of the matrix that we calculated. And this tau parameter was initialized to the values we found in the matrix. And then a bucket for all other languages. And notice this K is flexible to being 5, 10, 20, whatever you want, depending on how much data you have. We initialized it to 5, the 5 closest transfer languages. And then this S function, there's a new lambda for every single one of these. But basically, this is a way of modeling the diminishing returns given the amount of unique tokens for that language and the amount of tokens you've trained on that might be more than unique. So if you've done more than one epoch. So this is our scaling law. And obviously, we tried many things and we tuned this. And to see a breakdown, the learned parameters are in red, the blue are given, and we were able, D, E, F would be Thai plus the contribution of English plus Indonesian, Malay, Croatian, Spanish, plus a bucket for everything else. And basically, I'll skip over this for interest of time, but we evaluated by holding out the largest models and then separately the largest data or the largest compute or separate multilingual mixtures that had never been seen before. So I think this is a very fair way of evaluating it, more fair than some other scaling law papers have done in the past. And basically, we get state-of-the-art results. There's not a lot of competition, to be honest, but we were really proud of these results. And we did some ablations, and it allows you, although we didn't publish it in the paper, to reverse engineer based off the fitted law how to get the best mixture for a given language based off of everything you've observed. So that's the first part of the paper. I want to get to, or the first two parts. I want to get to the next two, but any quick
Question.
questions on this? Yeah.
Yeah, so I guess do you need to do this? Like, how different is the fit the scaling law and decompose the optimal split for Thai, as opposed to just look at that heat map that you made earlier and like pick only the ones that seem to have positive transfer and then mix them in the ratios that the scores suggest?
Oh, good question. I didn't do that specific like weighted heuristic. But honestly, I would trust the fitted scaling law more because it takes into account model size, whereas your heuristic doesn't. So your
Yeah.
heuristic is only working for 2 billion parameter model size,
Okay.
whereas this will scale how this works for model size.
I have two questions. So
Yep.
first, in line of the first question, you mentioned model size, like how different would the mixture be with respect to model size because you brought it up. And I guess the second question is like, how inherent is this study multilingual? I find it could be like multi-domain. Like, how do we mix code, general, like literature data when we want to optimize for math tasks? Like, that feels like the multilingual setting over here.
Yeah. Um, we for the first setting, you asked if we increase the model size, what happens? And basically, the synergies between languages improve because there's more space in the model for them to learn from one another rather than them competing for space, the curse of multilinguality, if you will. So we actually see, it varies, but you actually are more likely to upsample more heterogeneous or other languages than you are if the
I see.
model is very small. Um, the for your second question, if sorry, remind me your second question.
Like how specific is this a multilingual
Oh
question?
yeah.
Because you could just choose different domains, right?
Yeah, I love that. I absolutely think these methods could generalize if you had some initial compute, and I'm confident the big labs are doing this to figure out their preliminary mixtures as well.
Mhm.
Um, yeah, I do think that you could split up data, honestly, any way that you want, and try to understand the benefits of different things. Multilingual is one natural way, but there are many others. Yeah. Um, How much time do I have left out of curiosity, just so I can tailor it?
Like 20 minutes?
Okay, perfect. So I want to leave time for discussion and questions, but there were two other pieces of the paper. We did a lot. There were a lot of analyses that we didn't do because there's so much you can do with this data, but there were a couple more that we thought were really applicably useful, at least from what we were hearing in Google and to people actually developing AI systems. Um, and One is, there's a question if there's already multilingual models released, massively multilingual ones available, you can just fine tune for your target language. And that's so much more computationally efficient or continuously pre-train than it is to pre-train something from scratch. So the question is, what should you do? Should you do one or the other based off of a certain amount of compute? And we're actually able to test this. So basically, what we have here, this is for English, is the dotted line, or sorry, let me say this dash line is the loss, the training curve, when you start from a multilingual model and you continuously pre-train just in English. And obviously, it already is a pretty smart model. It's been pre-trained in many languages, so the loss starts low and it stays low. But if you look at this dotted line, this is the line of something pre-training from English for English from scratch. And basically, it surpasses or gets better than the fine-tuned model because it is specifically for the target language. And the question that we had in mind then is, okay, so if you at low compute, you should fine tune, but at high compute, maybe you should pre-train from scratch. And the question is, what is the inflection point? And it's very different for these different languages. This is the number of tokens that it's seen. And, by Chinese, it's about 280 billion, but by English, it's 144. But if you look at different model sizes, we can actually roughly, very roughly, create like a formula for it that shows here's the inflection point. And if you have more compute than, basically, this is your model size, you plug it in. If you have more compute than that, then you should pre-train from scratch. And if you have less compute than that, it might be better to just continuously pre-train off of the model you have. And the model that you start with, we always made it a, I'm trying to remember, it was overtrained multilingual Unimax model. So obviously it depends how good that underlying base model is, but we tried to train all the different sizes so they were pretty good starting points that were somewhat similar to what you would see in released open weights models in Hugging Face. So yeah, any questions on this piece?
Pretty straightforward. Yeah.
Looks good.
Cool. All right. So the very last piece of the paper was inspired by the question. There are teams that had, rather than like one big multilingual model, they had smaller models that were trained for like K languages. And maybe it's like a, 4-language Romance language model. Maybe one was like a Asian cluster of models, or, I don't know, Middle Eastern, some like similar language families would be clustered into small models. And so they're faster inference and more catered to that individual domain. And so they asked, what happens if, now we have better data, better curation, and we want to increase the number of languages supported by this model from, let's say, 4 languages to 8 languages. But the worry is that the performance would decrease in the original 4 languages. So if you were to sample evenly across them, or it's an assumption, it's not perfect, could you roughly tell us how much more compute you'd have to dedicate, or how much bigger the model would have to be, or how much data you'd need, more data you'd need, in order for increasing from K to 2K languages to not reduce the performance on the initial model, initial languages? And so to figure this out, a little bit more of a complex problem, we wanted to create a new scaling law and fit it where it was parameterized specifically by the number of languages K. And so after thinking a lot about this, I went with this formulation because there remains symmetry between the chinchilla symmetry between the effect of the model size and the effects of the data. But also they get to interact with the number of languages. And if phi and psi are 1, this simply reduces to chinchilla. And so it gives them lenience to move around and basically see what is how does the size of the model affect the scaling of the number of languages, and vice versa, and for the data size, the equivalent relationship.
A question?
Yes.
Why do you have 2 different Ks? Because like each individual point in this comes from a particular run at a choice of a particular amount of compute and data points, right? So what is the phi and psi doing on the K over there?
You could factor it out at the A and B, but it'd be the same, right? Like K times A over 1 over NA, like you could just do this once, right? K here, parentheses. Yeah. I think it's...
No, but I guess so what's the difference between psi and phi in terms of K over here?
Well, we specifically want to figure out if psi and phi are different. Because if they're different, it says something about how the number of languages affects the model size, or its interaction with the model size is different from the data size. And it might say that as you increase the number of languages, you want to increase the model size more than you increase the data size.
Okay, I see. Yeah.
Yeah.
I don't want to detract, but how much time we have left?
We have like, I think we should let him.
Okay, let's keep going. Yeah.
Yeah.
Okay. I'm happy to talk more after about, but yeah. So if you crunch the math, you can analytically come up with a formula that says if you increase your compute from C to C prime, and that means you increase your total model size and total data size, and we figure out the optimal for each. R is 2 because we're going from 4 to 8 languages in this case. And in terms of the fitted law, it tells you how much we should increase the compute given how much we want to increase the number of languages. And then I will disclaim this is rough. Obviously, the which languages, the fact that we're uniformly sampling, there are constraints like that. There's obviously this is an estimate, and there are issues or limitations of it, I should say. But I think I wanted to tractably try to estimate or understand how it would model, and I did it individually for different languages as well. And roughly, we saw the same relationships. And this is sort of the aggregate relationship. And it's that if you want to go from K to 2K or K to 4K, and I'm just going to focus on, let's say, K to 2K languages. If you were to start at this model size and this data size, you should multiply the model size by 1.18, in other words, increase it by 18%, and you should increase the total amount of data by about 2/3, which actually means that you are increasing the each data from each language. So you're decreasing the amount of data from each language, but the total data is larger than it was before. Because we went from K to 2K languages, but rather than doubling the amount of data from each language, rather than adding in equal amounts of data for each language, we're actually reducing the amount of data we have for each language. But because there's synergies, it allows you to increase. Yeah. And basically, we computed this. I think it is a starting point and useful and interesting and tells you something about the nature of the curse of multilinguality and how much to increase your model size versus your data size along this optimal K line or curve based off of what we fit. So that's the presentation. So to summarize, we wanted to build Atlas to be a beginning help for developers that wanted to understand how to develop AI systems or scale them beyond English, where English is not the target. And we wanted to produce concrete scaling and mixing laws and synergy, empirical synergies between languages that developers could use as a starting point rather than their intuition or their guesses, basically, their speculation. I'm going to leave it there, but yeah, thank you so much. This has been phenomenal questions and great engagement with this. And so really excited to have you as an audience and appreciate your thoughts.
Well, thank you. Yeah. So we'll ask if there's none in the chat, but yeah, if for the people who are watching over Zoom, if you have any questions, feel free to unmute or you can just put it in the chat. So meanwhile, I guess I just have one, right? So I'm curious how this potentially changes when you no longer do 50-50, right? Because I think something about that, I guess, makes me ask a question, right? Which is, then it basically means that, so let's say you're doing Thai and English, you're sort of forcing yourself to have a model that's trained on a split, right? But potentially that's it's you need that restriction because you're looking at so many different languages and it doesn't always make sense to have 20% of one language, 80% of another, right? But potentially that's the situation where family might matter more than script, right? Where you have you're allowed to mix them at different proportions. And then maybe you have more similar languages sort of you can replace that in more, right? So Indonesian maybe can work as a stub-in more than Thai. So I guess at a high level, can you think of a way to study that a bit more systematically? Because I think the issue is that if you try to do that, the number of variations you can have explodes, right? So
Yeah.
because now you're not just like, you were earlier mixing them at a 50-50 ratio, now you can mix them in at whatever ratio you want, right? But like, let's say you cared about the downstream individual task language alone, and you're fine with having like varying proportions of your data set being of different languages, right?
Yeah.
I think your loss curves still do give that, right? It's just that your initial weight estimate on how you fit the function is highly determined by the 50-50 split, right?
Yeah. I mean, I think the final scaling laws look at all of the data. So all the way along, including the low data regimes, and not just bilingual, but also like um, multilingual mixtures of varying proportions. So the final scaling laws, I think their weightings might be a little bit more robust to that assumption than the matrix that we used as an
Yeah.
initial starting point. But I agree with you. It becomes very hard to figure out like an optimal way to do that. Um,
I guess like maybe to add on and clarify my question, it feels like the initial conditions set by the weights determine quite a lot, right? Because they determine what like makes the non-learnable parts of the function to fit, right? Because like the parameters for the section where like you're mixing in the similar languages, right? The ratios at which you weigh them is determined by that matrix, right?
well, this no, it's sorry, it's determined by the fitted scaling law, which only uses the matrix to initialize certain transfer parameters.
Oh, that's just the okay, got it, got it. And like I guess in your experience, to what extent does that initialization condition make a difference?
Didn't test for that, unfortunately.
Cool. Okay.
I yeah, that was not an evaluation that I did. Yeah.
Yeah, cool, cool. No, that makes sense. I think that clarifies it. Yeah.
In worst case, it doesn't matter at all, to be honest.
Yeah.
But
I mean, that's the best case, right?
best case for the scaling law being, yeah, fitting robustly, I guess. Yeah.
Yeah, yeah, yeah.
I had a question. So your last research question was about how many like K languages can you train given a model size and a data set size? But I think there might be an interesting confounding factor to study is when you have those K languages and they share a lot of script overlap. Essentially, what I think happens is that these languages compete for the same token IDs, right? So, for example, French and English, they might have the same token ID for a certain phrase, but actually in French it means one thing and in English it means another thing. So you can't easily pack K-related languages into a small model in the same way you could something that has more representation power, right? So I just wonder if like that's something you think is worth studying more, or if that's something you guys have thought of. I'm just curious.
Yeah,
Yeah.
absolutely agree with you. And I think what you're describing is the curse of multilinguality, right? Like multiple languages are competing for representational capacity within a model that is finite size. And that could be the vocabulary, that could be, the later downstream neurons, anywhere in the model. I think that to tease that out more specifically, whether it is vocabulary related or more like the neurons in the model, we would need to do concerted ablations that change one of those things at a time. But I do think my colleague here that like has thought a lot about the vocab stuff. I think that it's sufficiently large, and we did when we were doing these these last experiments, we didn't do a lot. That it was always languages in the top like 30 or 40. So nothing was like super underrepresented where they were, I think, overly competing. I could be wrong, but I think that like reasonable assumptions were made. But I agree with you. Like if that could be a point and is worth for the investigation for sure.
Yeah, because like, even if you have like more of a multilingual data mix, like the English byte pair will always win, right? And that'll always be matched first in tokenization. So, I think that it's unavoidable that you have that competition.
I guess I'm curious to see whether that's competition or actually helping, in that let's say you had two languages, right?
Yeah,
So
yeah,
let's say
yeah.
you fix the language model size,
Yeah,
and one is English and Spanish versus the other is English and Japanese.
yeah.
English and Spanish will have a much larger tokenizer overlap,
Yeah,
but potentially there's transfer in the logic behind it, right?
yeah, like the root language Latin.
Yeah, right.
Something
Like
like
I guess like which of those language pairings do you think will do worse? And in a fixed compute and model size regime, I think the English and Japanese does worse because I suspect the real bottleneck is not on the tokenizer side, but on the like neural representation side. But I don't know, Shayne, I guess you can tell me if that intuition is wrong or not.
Your guess is as good as mine. Good discussion. Yeah.
What about the K-phi and K-psi values? Because you were talking about how like that kind of helps you figure that out, right? Like whether it's really
Yeah.
like your data mix or like your size, representational capacity kind of thing.
Yes. Let me remind myself because it was interesting. Basically, where is it? I'm looking at the paper now. Phi is positive, but psi is actually negative, indicating a mild capacity-driven cursive multilinguality on the model side, but tempered by positive transfer across languages. And that's why you see like um, this asymmetry between how much you grow your model versus how much you grow your data
Gotcha.
when expanding. Yeah, and I think that's super interesting. It's like data has positive synergy. You don't need to grow it as much. Well, actually, that's not true. You don't need. I need to think about how to word this, but yeah, I'll review that.
No, thank you, thank you. Yeah, it's cool. Yeah.
Cool. That's it from me. Anyone? I think we have questions in the chat, which is, I think it's just can you please share the last slide?
I
But
think I did briefly. Yeah.
yeah, that's fine. Yep. Yep. Yeah, I think it's all good. Okay, thank you so much then.
I do have another question.
Yeah, go for it.
Yeah, I'm thinking about like a realistic setting where suppose I have multiple targets for multiple languages. Do you think like right now it is very easy to compute the best data mixture and how it scales with compute right now, just using your findings?
There are ways to do it. I haven't done it. But yeah, you can like optimize for the average loss because we're careful to like compute the loss for all 50 languages for basically like every experiment, even if it's like bilingual Thai and English, we're computing the Telugu loss. So like you could do some sort of was it you know distributionally robust optimize something fancy thing there, but haven't tried it.
Yeah, I guess my second question is like for researchers who do not have pre-training compute, do you think there is a way like to leverage, say, like a multilingual model's representation to how somehow like quickly give you an estimate of some part of your scaling law? And if there is, like, which part do you think that's doable?
It's a great question. I think that'd be a phenomenal area of future work. Like if you could, for minimal compute, take a model and somehow determine the optimal mixture based off of like just doing minimal fine tuning here and there. I didn't explore it, but I suspect there's ways to get most of the way there, or to do minimal pre-training, but to compute things. Maybe there's a way to like minimize what a compute you need to estimate what's best. But it goes beyond this work, to be honest.
Yeah.
Cool.
Awesome.
Thank you. Yep. I'll just cut this and then we can move on to our individual one-on-ones. Thank you so much.
Great to meet you all. And yeah, thank you so much for your great engagement and questions. And I'll jump in the one-on-ones and see some of you then. Thanks.